This paper and video abstract concerns the physics of patterned magnetic elements which exhibit shape anisotropy and are interacting via dipolar coupling. Controlling vortex chirality in hexagonal building blocks of artificial spin ice. Ideally, only 3 of the 6 magnetic elements that make up the hexagon should reverse its direction of magnetization, thus forming a vortex state. This is a ground state for the system. But despite this being the lowest energy configuration, and in the absence of disorder, in practice, this state is not always realized. The islands will switch their direction of magnetization in the presence of a magnetic field if the field exceeds that of the islands. Modified islands, of which there is at least 1 per hexagonal arrangement, require a yet greater external field to cause them to flip. These modifications may now be applied to achieve our desired target state. For the purposes of the present paper, the external field is never increased beyond switching field of a modified island. How can we check this scenario experimentally? In order to investigate the switching behavior of large arrays of up to 200 hexagons, we use the Swiss light source at the Paul Scherrer Institute in Villingen, Switzerland. Here, circularly polarized X-ray photons hit the sample, and the intensity of the emitted electrons allows us to determine the magnetization state, as in this example of a square platelet with closure domains. This technique is now applied to a sample consisting of many hexagonal structures of the type we looked at before. We see that, after applying a well-defined magnetic field, all samples are in the desired target state with a perfect switching probability for an array of 200 hexagons. This happens provided that some of the islands are modified, containing 3 adjacent narrow islands per hexagon. To switch a trefoil structure into a well-defined state with vortices is more challenging but still feasible if the narrow islands are chosen appropriately. In absence of narrow, modified islands, the switching rate would be close to 0. Our numerical simulation data show that the hexagonal arrangements may be brought together, almost touching, before the realization of target vortex state begins to fall off. If we would have considered rings with islands of the same width, we would never achieve such a high reliability. In fact, we observed it as low as 10%,
numerically,
or 31%,
experimentally.
The hexagons, which form a ring-like structure consisting of single-domain elements, are scalable down to arbitrary length scales.
In conclusion,
we have shown how it is possible to drive into their lowest energy state systems of single-domain particles arranged in patterns of 1, 2, and 3 adjacent hexagons. Reliable switching is achieved by tailoring the island's anisotropy, thereby overcoming the inherent disorder of the system. By selective modification, the systems are made so robust that individual hexagonal arrangements may be brought so close together as to be almost touching before there is a breakdown in the formation of target vortex states,